Okay, so in the previous video, I was talking about the variance of these beta parameters. And in particular, I talked about homoscedasticity and heteroscedasticity of these beta parameters variances. And we saw that although these beta parameters, that is the average effect of particular x variable on y, it is unbiased estimator, the variance is not an unbiased estimator if the assumption of homoscedasticity is not met. That is, if the variance across all observations is not constant. And it is important that we understand the concept of variance of beta j, because a larger variance means that our estimates are less precise, and this translates to a larger confidence intervals and less accurate hypothesis testing that we will see in the next chapter. That is why it is important that we take care of this variance. So the first thing we need to understand is like, how is this variance calculated? This was the model that we estimated, and all these beta parameters represents the impact of that particular x variable on y variable. And we are interested in calculating the sampling variance of all of these beta parameters. So beta j means j could be 1 up to k. The variance of any slope parameter or beta hat, it is calculated using this formula. So what this formula is telling us is there are three components that goes with the variance. The first is the error variance, sigma squared or error variance. This is positively correlated with the variance of beta j. It implies that as sigma squared goes up, the variance will be high. Right? It means that there is more noise in our equation. It is difficult to estimate the partial effect of any of the independent variable on y because of the higher variance. Now, since we want to make our estimates as precise as possible, that is, we want to minimize these variances, so we need to decrease the variance of beta j by decreasing the error variance. And to decrease error variance, we have to include more x variables on the right hand side. That is, include more explanatory variables on the right hand side. So that was the first component. The second component is SST, or the sample variation in the xj variable. Since there is a negative relationship between SST and variance of beta j, it means if SST increases, variance of beta j decreases. That is, if we want to come closer to making the precise estimates of beta j and we want to reduce our confidence intervals, we have to increase SST. You have already seen this SST in some of the previous videos. But the idea here is that to decrease variance of beta j, we need to introduce more variation in the data. And to do that, we need to increase our sample size. We need to include more observations in our data set. For example, if you have 30 observations in the data set, by including more observations, say by increasing the number of observations to 50, you can increase SST and also decrease variance of beta j. And the third part of this equation is r squared. It is not the r squared that you get by regressing y variable on all these x variables. Rather, it is the variance that you get from estimating xjth variable on all the remaining x variables. That is, if you regress x variable on the other variables, then this is the r squared that we are talking about. As an example, if you have a simple model of only two parameters, then this r squared is that you will get running x1 on x2. So as you can see here, there's a negative relationship between variance of beta j and r squared. That is, if you increase r squared, variance of beta j will go up as well. So this is because this is 1 minus r squared, and we know r squared is between 0 and 1. So if this r squared increases, then this term will come closer and closer to 0, and variance of beta j will go up. So what this means? This means that x1 and x2 are highly correlated, And as r squared increases to 1, variance of beta j get larger and larger. That is, the high degree of linear relationship between x1 and x2 can lead to larger variation for the OLS slope parameters. And the smallest variance of beta j is obtained when r squared is very close to 0. So this is what we want. We want these two variables to be uncorrelated with each other. So the higher the linear relationship between them, the higher will be r squared. But this is what we don't want. We want to bring this r squared as close to 0 as possible, which means we want all these x variables on the right hand side to be uncorrelated with each other. And this will happen if and only if xj has 0 sampling correlation with every other independent variable. And in anher extreme example, if r squared is equal to 1, this means that xj is a perfect linear combination of some of the other explanatory variables in the regression, and the variance of beta j will go to infinity. So our goal is to decrease r squared, that is the correlation between x variables. To do that, we need to bring all these x variable in the model, those are uncorrelated. So this is how we calculate the variance of any beta parameter by using three concepts. The first is the concept of error variance, that is how far away our predicted values are from our actual values. And we want to decrease error variance to decrease variance of beta j. And we want to increase our sample variation in xj by increasing our sample size so that we can decrease our variance. And the third component was this r squared, which is the correlation between x variables, and we want to minimize that correlation so that we can have a minimum variance. So the goal here is to minimize the variance of these beta j parameters so that we can have precise effects of any x variable on that y variable. So this was a little bit of theory behind the variance of these slope parameters in relation to these three factors. Most of the things will be clearer to you in the next chapter when we'll talk about the variance of these beta parameters in relation to t-values and how it affects the statistical significance of these beta parameters. Alright, I'll see you in the next video to talk about the variance inflation factor.